they're all old hands at these subjects, and I don't want to get into the subject. I don't know anything about it. I know the mechanics, that's all. What they do with the mechanics is their problem and your problem. But under this TechIP umbrella, what we had started off around 2012, right? 2012, with a small hope that we could contribute together to improving the quality of higher education in India. And towards this, we, a group of us, about 10 or 12 of us, had grand plans. Grand plans included undergraduate curriculum, postgraduate curriculum, labs, this, that, setting up of these cluster facilities so that with high-end equipment which could be used by various colleges in the neighborhood, all those things. Out of the grand plan, we could achieve a small amount of things that we thought we wanted to do at that time. And part of it is this thing where we had a continuous set of courses being offered based on demand. A lot of them were based on feedback at various levels. And all these courses have been nicely collated and put in video form in our website. So everything, every lecture, every single word spoken in a lecture is there on varied topics. Mechanical engineering being very intense, many areas in mechanical engineering were covered, and similarly electrical, computer science, and so on. So I would also urge you to urge your students to look at these lectures, because these are really excellent lectures given by people who know their subject from across the world. It's not only here, from across the world. Okay. And that was one thing that we believe has been our achievement, together with all of you. TechIP, as you know, is going to come to an end. In October, we are going to wind up this part. Government of India has new plans, which unfortunately does not include all colleges. It is now going to be focused in the hill states only. Okay. Whether we are going to be part of it or not, we don't know. It completely depends on whether we want to be. Okay. But till October, we hope that we will continue getting inspired by you and having these fruitful interactions, discussions, through which you will learn and then pass it on to your students. The main thing is passing on, okay, so that the whole learning experience gets enriched. And also the other thing that we wanted to emphasize through this was connections, that establish connectivity amongst researchers, amongst yourself, because you come from different parts of the country, and with people here, so that being not so monetarily enabled country that we are, whoever has good resources, those resources can be made available to all. So if we have something very good here, you should be aware of it so that you can use it if you want to, and similarly with other places. Okay. So let's hope that we achieve all those things, and I'm sure that my colleagues here will actually take you through a grind with you getting these urges to start bunking. Please don't do that. Okay, after some time. Okay, this is a habit that doesn't go from student days; it stays. Huh? So all the best. And by the way, any complaints you have with respect to housing, food, Mrs. Wahi is there. Mrs. Wahi is there. Professor Wahi is here. So you can catch any one of them, and feel free to let us know. Whatever we can do, we'll do. Okay. Thank you. So Mohit, it's all yours.
All right, so that was important. We can keep talking over the breaks and so on, but let's give you an idea of what this workshop is about. Okay? So let's assume we want to manufacture a machine, a nice component like this, which is part of a turbine engine. Yeah? It's got free-form blades, very nice geometry, very difficult to cut. And let's imagine you want to make many of these. Yeah? So not just one, but you want to process this and make multiple parts like this. So how would you go about it? Yeah? So typically you start with a CAD model, if this works. Yeah? So you start with a CAD model, yeah? And of this geometry that you want to build. Depending on that CAD model, depending on what kind of operations you want to perform, you'll select tools. Yeah? It might be drilling, boring, milling, and so on. In milling you might have tens of tools, so you select those kind of tools. depending on the size of this object that you want to make, then you'll select a machine. Yeah. So once you've done tool and machine selection, you'll probably go and build, take it to the CAM environment, the computer aided manufacturing environment, where you will generate a tool path. You'll describe cutting parameters for each tool, and you'll try and generate an NC tool path. Most of this is empirical. This depends on how you understand the process. Once you build that tool path in the CAM environment, you'll take it out, you'll post-process it, you'll convert it into a G code or an NC code, you'll load it onto a machine, and you'll cut. Now, if you're lucky, or if you have a lot of experience, you might be able to do this first time right. But more often than not, you have some problem with, all right. So like I said, if you're lucky and if you have a lot of experience, you might be able to engineer the process so that the first part that you will make will come out nice and clean, as you can see in the bottom. So these are blades that you machined. But because this approach is empirical, it's based on somebody's vast previous knowledge, or based on some design data book, handbook that you will pick up, it's not always optimal, and it's not always guaranteed that you will make the product that you want with whatever tolerance specifications you want and with whatever productivity requirement that you set, so in terms of optimal machining time. And more often than not, what might happen is you might result in what we call chatter vibrations, which we'll talk about a little, but chatter is a very non-linear large amplitude vibration, and it destroys everything. So because this approach is empirical, you'll probably go through several iterations to try and avoid this. It's very rare that you will end up with the first time right solution like this. And because you want to make multiple parts like this, you want to try and engineer your process so that you have optimal cycle times in terms of programming, as well as part surface quality and tolerance requirements that you can meet. Now, say for example, if you chatter and if you destroy the part, this is a very high value part, it can cost thousands of dollars or lakhs of rupees. Typically what you would do is to try and avoid this is iterate. You will play with your tool parameters, you will play with perhaps your tools, you will probably play with your machine. Try and change one of these many things to try and get a nice optimal cycle time with good surface quality. And you will do this in several iterations. Again, if you are lucky, you might get this, but it's very unlikely that you will get this. So what you'll probably do is call your tool supplier, Kenner Metal or somebody else, and ask them what the problem is, why is this chattering? And he will give you some input based on their vast experience. You try this tool with this combination of cutting parameters, maybe you might solve the problem. If that doesn't work, you'll probably trouble the machine builders. You'll probably call EA or whoever is building the machines. And you'll ask them, what is the problem with this machine? Why is this thing chattering? Why is it destroying my part and not giving me productivity? And again, if you're lucky, you will reach whatever you want, but more often than not, you will not. So the question we ask ourselves is, what is limiting productivity? What is destroying part surface quality? And that brings us to this notion of machining dynamics, which is what this workshop is about. So machining dynamics is this combination of dynamics of machines, so how machines vibrate, and the machining process, and how these things interact with each other. Now, everything in the world is flexible. Everything vibrates, whether you like it or not. It wants to vibrate, it's its happy state to vibrate actually. And a machine is no different. And a machine is no different because it has got a source of excitation, something that is making it vibrate, which is the cutting force. So cutting force is enough energy inside it. So when you're cutting, so as in when you doesn't matter whether you're turning, boring, drilling, milling, there is force generated. That's how you create, that's how you shear and you evacuate the material or you remove material. And this has enough energy in the system to try and excite something in the machine, so make the machine vibrate. Now when the machine vibrates, as you can see in this nice animation which somebody has taken a lot of effort to build, so this is the vibrating tool and this is a rotating workpiece and turning. Ideally you want this chip thickness to be constant or static. And we'll get into details of all this later. This is just an overview. You want this to be static, but because the system is flexible and because it's vibrating under the action of cutting forces, that chip thickness is no longer constant. You can see it's modulating. And this modulation tends to grow, yeah? Because what happens is the forces make the machine vibrate, the vibrating machine changes this chip thickness, that changes the forces, which again changes the chip thickness, and this becomes a closed loop system, which can become unstable very easily. And sometimes when the vibration, let's put it the other way, yeah? Sometimes when the energy, yeah, diverted from the machining process because of this modulation, when this energy is greater than the vibration damping capacity of the system, these vibrations grow and become unstable, and they result in what we call chatter. Now chatter is I think Professor Vai already mentioned, a non-linear phenomenon. It's large amplitude, it will destroy your part surface quality. For example, you saw that turbine blade which I showed you in the previous slide. It will destroy that part surface quality, it will probably break your tool, it will damage your spindle, your bearings, and sometimes even your machine structure. So at all costs what you want to do is avoid this chatter. And as in why it becomes difficult, this is always happening. Yeah? There's always the cutting force, whether it's turning, milling, drilling, boring, sawing, doesn't matter. And there's always something that is flexible in the machine. So this interaction is always taking place. So the question is, what do you do? How do you avoid these chatter things? Now fortunately for us, yeah, we understand some of the machining processes, some of the many. We understand its process physics, we understand how machines vibrate, and we can try and understand and build models as how these things interact with each other. So this is machining dynamics. Yeah? And if we understand how these things are interacting with each other, we can construct what we call stability lobe diagrams. Now this is a very important and interesting piece of information. Yeah? I'll just talk you through this. So on the x-axis, we have spindle speed, yeah, RPM. On the y-axis, you have limiting depth of cut, how deep you can cut. These lobes that you see, or these curves, are what we call stability lobes. Everything below this lobe boundary, if you select a cutting parameter, say 2 millimeter depth of cut at 10,000 RPM, it is below this. It's going to be stable vibration. But if you select a parameter, say at point A, yeah, which is say at 6 or 7 millimeter depth of cut with about 15,000 RPM, it is in the unstable region. Yeah. So you will see, if you see measured force signal, yeah, or microphone signal, it's large amplitude vibration, and you can see it destroys part surface quality, it's chatter. You can move from an unstable to a stable regime, yeah, if you understand how these things work. So if you have metrics like this or a stability lobe diagram like this, you can go from unstable to stable or stable to even more stable. Now you will see this chart over the next 5 days plenty of times. So if you've not seen this before, this is just an idea as to what we're getting into. Now this is very non-intuitive, yeah, and it's very difficult. So even for people like us who think we understand it, so when we were setting up the labs for this workshop, yeah, we also chattered, we also broke tools. Yeah. So we did not expect, I don't know if you can see this here, we did not expect to see chatter when we were setting up the labs for this workshop. But we saw severe chatter and we broke the tool and almost damaged our dynamometer also. Because when tool breaks, it's going to damage things. So the point of showing you this is very non-intuitive, very difficult to do, but hopefully we will try and equip you, yeah, with the fundamental understanding of machining processes and dynamics and this interaction, so you can understand what is happening and how you use this information. All right, so this is a very nice video, yeah, to show you how things chatter. Yeah. My laptop is very old, and that is why it doesn't load properly, but maybe I can load it separately. This is a high-speed camera of image of chattering that some of our collaborators, in fact Professor Vai's collaborators, Budapest, yeah, they acquired these videos. Yeah. Okay, so this is showing you how this is an end mill. Yeah? Perhaps some of you might have seen it. This is an end mill, and it is showing you how it is vibrating when it is not supposed to. This is several kilohertz of sampling rate or high speed camera, and you can see that it is leaving these waves on this surface. Yeah? It's not very clear from this view, but you can see that this is happening. This is not supposed to vibrate. It is vibrating. Yeah? Perhaps another image might make it, another video might make it clearer. So these videos are from Professor Gabor Stepan in Budapest. Yeah? He kindly shared them with us. Very difficult to acquire. Yeah? So this is the bottom view. Perhaps this makes things clearer. Yeah? You can see the tool is vibrating and is leaving these waves on the surface, which it is not supposed to. It's supposed to be a nice clean cut. Yeah? And you can see as time progresses that the vibration behavior changes. During one rotation it is stable, during another rotation it is unstable. And this is what we want to avoid. Yeah? Because if you let this continue, it will damage not only your part but break your tool and spindle and so on. So what is it that is happening behind in the background is what this workshop is about. Yeah? Okay, so returning back. Yeah? So the idea is this machining approach that you had of doing empirical trial and error, trying to talk to your tool supplier, machine builder, whoever, or your wisdom of empiricism, and try and result in situations which are always stable. So what we would like to motivate is a physics-based approach to manufacturing. Understanding what is happening in the background, understanding the process, understanding the vibrations, understanding interactions, so that you can always result in a stable, highly productive, engineered process. So that is one of the objectives behind this workshop. Okay. Like I said earlier, this is very non-intuitive. These are again the same stability lobe diagram we showed you. Region above is unstable, region below is stable. This is the boundary. Now this is so non-intuitive. For example, when you chatter, yeah, or when it starts vibrating large amplitude, most people become conservative. So instead of, as in they tend to reduce cutting parameters. So from going, if you're at point A, most people will end up reducing the depth of cut and even reducing the spindle speed, because you're scared, you don't want to break things. Yeah? And which is completely understandable. But what we want to try and motivate is that you don't need to reduce and become conservative, you can become more aggressive. Yeah? And you can see that your productivity or the volume of material that you remove is a function of your depth of cut, your width of cut, which is constant in this case, and feed. Feed is again is a function of spindle speed. We'll talk about these things. Yeah? But instead of being conservative, you can be more aggressive if you understand exactly what is happening. And why this is really relevant is if you take two examples. Yeah? This is a large aerospace structural component, aluminium, and this is a turbine blisk. This starts with a raw material weight of 2 tons, 2000 kilograms. Its finished weight is 22.7 kilograms. That's a 99% volume removal. Yeah? 99, that's huge. Yeah? And it's all done through machining. And if you end up chattering something like this costs lakhs of rupees to manufacture. Several hours, not hours, weeks of machining time to do this. So the idea is if you know something like this, yeah, you can use this information to be more productive, more aggressive, without breaking and damaging the part. Similarly in blisk manufacturing. Yeah. Again, this is a very high value part, costs several lakh rupees to manufacture. This is Inconel, yeah, also very difficult to cut. But if you can create these things, understanding the process physics behind it, you can do such things. So again, that's one of the motivations behind this workshop. All right, so there are 3 things that go into these things. We'll talk about into creating these process machine interactions and building machining dynamics models. There's machining process models, which we will talk about. There's the dynamics, which we will talk about, and of course, partly what kind of tools and workpiece materials that you will use to try and build these interactions so that you can always guarantee stable cutting conditions. So this is the overall objective. There will be 3 modules which I talk about a little later. But this is the grand objective, or 3 grand objectives. So firstly is to introduce to you what these ideas are of machining dynamics, with the aim of doing virtual manufacturing. So everything is process physics based, simulation based. You do these things before you go to the machine and cut. No trial and error. First time right, through understanding what is happening. And like I showed you those 2 examples, yeah, it becomes very relevant in critical applications or high volume removal material that you want to do. We'll have lab sessions, so everything that we'll teach you in class will have lab sessions, so you will see how these things work. Of course, one of the major objectives of this is to introduce these topics to you, to motivate you to perhaps share these ideas with other people in your universities and wherever else you're coming from. So we'll go through fundamentals of machining process modeling, we'll go through fundamentals of dynamics of machines, how things vibrate, building ground up these models, and then the fundamentals of process machine interactions. Now, all of these three things I think is very relevant, given the current environment in India. So if you see, as in we are adding millions of people to the workforce every year. And in my view, the only way you can absorb these millions of people who are coming into the workforce is by giving them productive employment. And for that you need industrialization. And the backbone of any industry is the capital goods industry, which is the machine tool industry. But in India, most of our machine tool consumption or even cutting tool consumption or defense consumption is imported. We import about 75% of our requirement. So the idea is, if you can engineer these things, if you can develop the technology here through teaching you, for you to teach your other people, to train this manpower that is necessary for this indigenization is also one of our objectives, yes, is to introduce these ideas so you can carry it forward. Because each job that you add in the capital goods industry has a multiplier effect. So one job here, one technical trained manpower that you will create when you go back and introduce these ideas to your people can have a ripple effect of, or a multiplier effect of 5 to 6. That's one of our objectives. Yeah? All right, so this is 3 modules like I said. There's a machining process module. We'll talk about orthogonal cutting, oblique cutting, milling processes, which is also very important. We'll do experiments for each of these so you understand exactly what we're talking about. So we'll model and then experiment and predict and measure. The same thing with vibrations. We'll do single degree of freedom systems, multi-degree of freedom systems, and we'll do experiments for you to appreciate how to measure dynamics for machines. And of course, we'll introduce these chatter models, yeah, turning, milling, and of course, micro milling. So this happens even in micro milling. Yeah? It's a very different phenomenon, very different effects, but we'll talk about those also. And we'll also have experiments to demonstrate to you how to measure and avoid these things in the labs. Yeah? We have a list of speakers, experts actually, 2 of whom are already here. Yeah? For each module. We have Dr. Chaudhary who will talk to us now about machining processes. We have Dr. Shakti Gupta who will join us tomorrow, who will talk from IIT Kanpur, who will talk about vibrations. So he'll introduce fundamentals of vibrations. There's Mr. Mohan Ram, who's from the Indian Machine Tool Manufacturers Association in Bangalore. He is the senior scientific advisor to the government. So he will talk a little about industry perspective and what they need. Perhaps that also might be relevant. And of course, the main focus is process machine interaction. So that's where a bulk of our speakers are. There's Dr. Wahi, who's already here. There's Dr. Ramesh Singh, who will join us from Bombay. He'll talk about micro milling. There's Dr. Ganguly from IIT Delhi, who will talk about control of machine tool vibrations. There's Dr. Ramkumar, who will also talk about sensors and actuators for machines. And there's of course Dr. Jin, who's an expert in micro milling and dynamics of micro milling. He'll also be here. At the risk of sounding immodest, I would say that this pool of people is like an ocean. And what information you want from them is up to you. If you come with a spoon to collect information, is up to you. If you come with a mug, is again up to you. Or if you come with a pump, information is limitless. So feel free, not only limited to machining dynamics, but if you want to talk to anybody else about anything else, please feel free. You're here to try and build that association also. And I think everybody is available all the time. Yeah? This is an overview of the schedule. I think everybody already has a copy of this. Yeah? It's like I said, it's going to be very intensive, very math heavy. Yeah? Everybody has notebooks, yeah? But like Professor Upadhyay said, everything is video recorded. Yeah? So even if you don't take notes down, you can go back home and you can watch these at your leisure. And we encourage you, in fact, not only watch them but also share them. So with that, of course, we have a dinner on Thursday, the Bada Khana. Yeah? So everybody's got to be here for that. With that, that's what I have to say about the overview. We can start with a lecture session with Professor Chaudhary.